This segment we're going to talk about ideal gas mixtures. Up until this point we have talked about single component systems. So our working fluid has been water, maybe it's been a refrigerant, but the same molecule makes up the entire working fluid. So there's one molecule found or one type of molecule found in that working fluid. We have talked about a multi-component system, and that's air, but that's very specific, and air is very, very common. Makes sense for us to make thermodynamic properties for air because we have a lot of it and we deal with it a lot. But what if you have some random mixture of gases? Doesn't really make sense to make thermodynamic tables of properties for those unless you're using it a whole lot. So how do you deal with that? Well, that's what we're going to talk about. We'll talk about two cases: mixtures of non-reacting components, and that would be the case if you have HVAC applications in which you have moist air, which is composed of two components, air and water vapor. We'll talk about if one of those components condenses out. So for example, if you cool moist air to a certain temperature, your water may condense out. And we'll talk about how we know whether there's condensation and that sort of thing in a few segments. We'll also talk about what we do if we have mixtures of chemically reacting components. So with that air and water vapor, you started with air and water, started with dry air and water, and you ended up with dry air and water. But with a chemical reaction, what you start with is not what you end up with. So for example, in combustion, you start out with air and fuel, and you end up with something else, some products of combustion. We'll talk about what those products are and how we know what those products are when we get there. All right, so we need some way to describe the composition of our mixture, and we can do that in terms of mass or moles. You've probably not talked about moles since chemistry, and that's okay. All you need to know is it's a certain amount of something. You may remember that number 6.023 times 10 to the 23rd. Well, a mole is 6.023 times 10 to the 23rd of something. So a mole of water is 6.023 times 10 to the 23rd molecules of water, for example. So you don't even have to remember that number. Just kind of keep that in your back pocket, that it's a certain number of molecules or whatever you're talking about. All right. So the mass of the mixture is M, and you'll notice that I wrote it two ways: without a subscript and with a subscript. Your book leaves off that subscript M, where M stands for mixture, the subscript. Some people like to have it on there when you're talking about mixtures. Some people like to leave it off. So I typically leave it off. I think it looks a little bit cleaner, but sometimes I'll write it both ways, just so that it's completely clear what I'm talking about, that I'm talking about the mixture as opposed to the component, because it'll be important to keep that straight, and you'll see that as we go along. So the mass of the mixture is equal to the sum of the masses of each individual component, and you'll see that the subscript I indicates the component. It's just a generic subscript for the component. The number of moles in our mixture is equal to N, and that's equal to the number of moles, the sum of the number of moles of each component in your mixture. Sometimes it's useful to talk about the ratios of each of those things. So the mass fraction, MF, is equal to the mass of the component over the mass of the mixture. And you can see the sum of the mass fraction of each individual component should be 1 in that mixture. You can also talk about the mole fraction, and since MF was already taken, we use Y, and this is the number of moles of the component over the number of the moles of the mixture. And you can see the sum of the mole fractions in your mixture should be equal to 1. There will be a need to go between masses and moles quite frequently, and so if you need to go between those things, the molar mass is your friend. So that's capital M. You see that I've written this relationship in terms of, or applied to the mixture, so it's the mass equals the molar mass times the number of moles. Now, if you have a component, you can just look up that molar mass. You have those in table A1 and A1E, but if you have a mixture, you need to calculate that, unless it's a really common mixture like air. So the way that we do that, we define the molar mass is equal to the mass over the number of moles. And then I look up at the definition for the mass of the mixture up in the left-hand corner, upper left-hand corner, and I see that the mass of the mixture is equal to the sum of the masses of each individual component. Then I write the mass of the mixture, or the mass of the component, in terms of its own molar mass and the number of moles of that component. And then I look at this guy and I say, oh, well, the number of moles of the component over the number of moles of the mixture, this is just equal to the mole fraction. So now I have another equation that I can use to calculate the molar mass of my mixture. I can also apply that relationship that relates the molar mass and the number of moles. I can apply that to the component as well. And remember, you can look up those molar masses for the components in Table A1 and Table A1E. All right, so we are used to getting property data on a per mass basis. We're used to looking up H values, for example, but you may have noticed that there are tables that have H bar values. These are just on a per mole basis. So it'll be kilojoules per kilomole or BTU per pound mole, and you can find these for 5 different types of commonly used gases, especially when we talk about combustion in Table A23 and A23E. Often we assume that these mixtures of gases behave as ideal gases. So the mixture behaves as an ideal gas and the components behave as an ideal gas. And that's an assumption that we're going to make for the rest of the semester for these types of gases that we're talking about, or these mixtures that we're talking about. So you can apply the ideal gas law to the mixture or the component. So here I've written MRT equals PV, where that R is the specific gas constant, and we just need to remember that R is equal to R bar over the mass. So you can see that relationship M, the mass, equals the molar mass times the number of moles. It still sort of applies. So you've got something written in terms of mass, and you're using the molar mass to go between mass, things written in terms of mass and things written in terms of moles. And that universal gas constant you can look up, and there's several values that are given to you at the bottom of your conversion factor sheet in the thermodynamic tables. All right, so I can also divide through by mass, put things in terms of specific volume. I could also put things in terms of the universal gas constant. And you see that it looks exactly the same, except what I've done here is I've written the specific volume, or the molar specific volume, which has a little V or a little bar over it. And instead of being written in terms of mass, it's written in terms of moles or kilomoles. So if you see a bar over it, over that property, it's not in terms of mass, it's on a per mole basis, or per kilomole or per pound mole basis. You can also apply that ideal gas mixture to the component. So here I've just put a little subscript I after every single one of those. I can also divide through by the mass of the component, put it in terms of specific volume. And I could do the same thing, write that molar specific volume. We typically don't use the molar specific volume, or I don't anyway, but I just wanted to put it on here just to make sure everything was there. All right, well, I suppose that's enough for today, and thank you for watching.